What if I told you that scientists can now take a simple skin cell from your arm and transform it into a beating heart cell, a functioning brain neuron, or even a piece of liver tissue? This isn't science fiction anymore. It's happening right now in laboratories around the world, and it's revolutionizing medicine as we know it. Welcome to the incredible world of stem cell research, where the impossible is becoming routine and the future of human health is being rewritten one cell at a time. Today, we're diving deep into the most groundbreaking advances that are bringing us closer to a world where damaged organs can be repaired, genetic diseases can be cured, and aging itself might become optional. Let's start with one of the most revolutionary breakthroughs in modern biology: induced pluripotent stem cells, or iPSCs. Think of these as cellular time machines. Scientists have discovered how to take ordinary adult cells, like those from your skin or blood, and reprogram them back to an embryonic-like state. It's like taking a specialized factory worker and teaching them to do any job in the entire company. This process, pioneered by Nobel Prize winner Shinya Yamanaka, involves introducing just 4 specific proteins into adult cells. These proteins act like master switches, erasing the cell's specialized identity and returning it to a blank slate state. Once in this pluripotent state, these cells can be coaxed to become any cell type in the human body. Heart cells, brain cells, liver cells, you name it. The beauty of iPSCs lies in their versatility and safety. Unlike embryonic stem cells, which require the destruction of embryos, iPSCs can be created from the patient's own cells. This means no ethical concerns, and more importantly, no risk of immune rejection when these cells are used for treatment. But creating these wonder cells is just the beginning. The real magic happens when we put them to work in regenerative medicine. Imagine a heart attack patient whose damaged heart muscle is beyond repair. Traditional medicine might offer medications or mechanical devices, but what if we could actually grow new heart muscle to replace the damaged tissue? This is already happening. Researchers have successfully used stem cells to regenerate heart muscle in patients with heart failure. In clinical trials, patients who received stem cell injections showed improved heart function and quality of life. The stem cells don't just sit there, they actively repair the damaged tissue, forming new blood vessels and restoring the heart's pumping ability. The applications extend far beyond the heart. For patients with spinal cord injuries, stem cell therapy is offering hope where there was once only despair. Scientists are using neural stem cells to repair damaged spinal cord tissue, helping patients regain sensation and movement. While we're not at the point of complete spinal cord regeneration, early results show that stem cells can bridge gaps in damaged nerves and restore some function. In the realm of blood disorders, stem cell transplantation has already become a standard treatment for conditions like leukemia. Bone marrow transplants, which are essentially stem cell transplants, can completely cure certain blood cancers by replacing the patient's diseased blood-forming cells with healthy ones. This approach has saved countless lives and continues to be refined and improved. But here's where things get really exciting. Scientists aren't just using stem cells as they are, they're editing them first. Enter gene editing technologies like CRISPR-Cas9, which work like molecular scissors and word processors combined. Before transplanting stem cells into patients, researchers can now correct genetic defects at the DNA level. For patients with sickle cell disease, this represents a potential cure. Scientists can take the patient's own stem cells, use CRISPR to fix the genetic mutation that causes the disease, and then transplant the corrected cells back into the patient. The corrected stem cells then produce healthy red blood cells, potentially eliminating the painful crises and organ damage associated with sickle cell disease. Similar approaches are being developed for cystic fibrosis, where researchers are correcting the faulty gene that causes thick, sticky mucus to build up in the lungs and digestive system. By fixing the genetic root cause, gene-edited stem cell therapy could provide a permanent cure rather than just managing symptoms. Cancer treatment is another frontier being transformed by stem cell research. While stem cell transplants have long been used to restore blood cell production after intensive chemotherapy, researchers are now focusing on a more sinister target: cancer stem cells themselves. Cancer stem cells are like the masterminds of tumors. They're the cells that drive tumor growth, spread to other parts of the body, and often survive conventional treatments only to cause cancer recurrence. By understanding and targeting these cells specifically, scientists hope to develop more effective cancer treatments that prevent recurrence and metastasis. Some researchers are developing engineered immune cells that can specifically hunt down and destroy cancer stem cells. Others are working on drugs that can force cancer stem cells to differentiate into less dangerous cell types or make them more vulnerable to conventional treatments. Now let's talk about something that sounds like pure science fiction: 3D bioprinting. Imagine a printer that, instead of ink, uses living stem cells to print three-dimensional tissues and organs. This technology is rapidly moving from concept to reality. 3D bioprinting works by creating scaffolds or frameworks onto which stem cells can grow and organize themselves into functional tissues. Scientists have already successfully printed simple tissues like skin, cartilage, and blood vessels. More complex organs like hearts, livers, and kidneys are in development. The potential applications are staggering. Patients waiting for organ transplants could receive organs grown from their own stem cells, eliminating the need for donor matching and lifelong immunosuppressive drugs. Burn victims could receive printed skin grafts that perfectly match their own tissue. Athletes with damaged cartilage could receive printed replacements that restore full function. One of the most fascinating aspects of current stem cell research involves understanding how these cells age and what that means for human longevity. As we age, our stem cells become less efficient at repairing and maintaining our tissues. This decline contributes to many age-related diseases and the general deterioration we associate with getting older. By studying stem cell aging, scientists are uncovering the fundamental mechanisms of aging itself. They're discovering that factors like cellular senescence, telomere shortening, and mitochondrial dysfunction all play roles in stem cell decline. More importantly, they're finding ways to reverse or prevent these changes. Some researchers are developing techniques to rejuvenate aged stem cells, essentially giving them a cellular fountain of youth. Others are working on ways to protect stem cells from age-related damage in the first place. These approaches could potentially extend not just lifespan, but health span, the period of life spent in good health. For patients with rare diseases, stem cell research represents hope where traditional medicine has few answers. Many rare diseases affect only thousands or even hundreds of people worldwide, making them economically challenging for pharmaceutical companies to address. But stem cell approaches offer a different path forward. By using patient-specific iPSCs, researchers can create cellular models of rare diseases in the laboratory. These models allow scientists to study disease mechanisms and test potential treatments in ways that weren't possible before. For some rare diseases, stem cell transplantation might directly address the underlying problem by replacing defective cells with healthy ones. The journey from laboratory discovery to clinical treatment isn't without challenges. Safety remains a paramount concern. Stem cells are powerful, and that power must be carefully controlled. There's always a risk that transplanted stem cells might form tumors or differentiate into the wrong cell types. Researchers are developing sophisticated methods to ensure that stem cell therapies are both effective and safe. Regulatory approval is another hurdle. New stem cell therapies must undergo rigorous testing to prove their safety and efficacy before they can be made widely available. This process, while necessary for patient safety, can take many years and significant investment. Despite these challenges, the momentum in stem cell research is undeniable. Every month brings new breakthroughs, new clinical trials, and new hope for patients with previously untreatable conditions. We are witnessing the early stages of a medical revolution that promises to transform how we think about disease, aging, and human health itself. The stem cell story is still being written, and we are all part of it. Whether it's through supporting research, participating in clinical trials, or simply staying informed about these incredible advances, we are all witnesses to one of the most exciting chapters in medical history. The future of medicine isn't just coming, it's already here, growing one cell at a time.